assume that our biomass is over 60% water. Hopefully we're familiar with what liquid water feels and tastes like. And if you brewed hot water for your coffee this morning or survived through a Canadian winter, you're probably familiar with the gaseous and solid forms of water as well. This phase classification of water is useful because within a given phase, the properties of the water are universal, say the density or the structure. Now, I'm a quantum information theorist, and other than to fuel my bludgeoning coffee addiction, I don't really work with water every day. Instead, I study microscopic or quantum systems. However, it turns out there's kind of a striking analogy between the two, where people smarter than me have found something called the computational phase of matter, where if I take any state within this kind of green universal phase, any state within that is this universal substrate to perform a quantum computation. Now, I was told that none of you are experts in quantum computing, so the picture that you can have in your mind is that if I take any state within that green blob, it's this canvas upon which I can paint out any beautiful arbitrary quantum computation. Kind of an analogy with the water, say I was trying to make a sculpture. If I tried to use liquid water or gaseous water, I'd probably have a very bad time. But I can take water, any kind of water in the solid or ice phase, and that's going to be this universal material I can use to carry out and create any kind of beautiful ice sculpture. Now, up until now, these kind of ideas of computational phases have been theoretical constructions and pretty well understood, but no one's actually been able to physically create them. So in my master's thesis work, I've been taking these ideas and trying to push them to a real physical realization. Now, I can't show you the copyrighted beautiful technological images that IBM has on their site, so you'll have to deal with my cartoon approximation here. But in my work, I developed algorithms for actually creating these interesting states in this universal phase on a real physical quantum device. Of course, these devices are still kind of being developed and very noisy, so I have to think about what are the most efficient ways to prepare them. And having prepared them, I can also try to develop algorithms to display what are the most efficient techniques for actually carrying out said computations. My research sits at the interface of this theoretical question of what gives quantum states their power and this more experimental physical realization of creating these in a lab and doing interesting things with them. And hopefully by unifying these two perspectives, we can answer this overarching open question in the field of what are interesting things we might do with quantum computers in the future. Thank you very much.